Hi guys, welcome back to my channel. Just kidding, that was a joke. My husband was teasing that I'm technically a YouTuber now because I've been posting these videos to YouTube for you all. And I thought that was funny. But anyway, let's go ahead and get started with this lecture. Today we're going to be talking about correlation. This lecture is going to have two parts. Part one will discuss the background information, get to understand what correlations are, and then in part two, we'll learn how to compute the R statistic and go through our, hypothesis testing steps. So you're going to need a calculator for that, as well as the bottom of page 2 of the formula packet. All right, so to get us started, bivariate correlations look at the relationship between two variables. Bi meaning two, variate meaning variables. So this method helps to support association claims, but not causal claims. We're saying that two variables, X and Y, vary together, but using this method does not allow us to say that one thing causes the other. A common phrase you often hear in statistics is correlation does not imply causation. Just because two things are related, associated, linked to each other does not necessarily mean that one thing causes the other. It's not that simple. But we still kind of use this type of language in our everyday lives, like one thing causes the other. If you take away one thing from this class, this would be a very important thing to remember. The standards for causation are pretty high. As we discussed in the claims and validities lecture, in order to establish causation, the variables do need to be correlated, but you also have to establish temporal precedence. One has to come before the other, and you have to rule out confounding variables. So nonetheless, correlational research is still a very useful tool. It is important to statistically demonstrate how two variables might be related to each other, the strength of that relationship, the direction of that relationship. And this is especially important or useful when you have a solid theoretical framework on which to base your hypotheses. All right, so how do we demonstrate correlation? We can use scatter plots. That's when we have our two variables on a graph and we can plot each data point, or we can calculate the statistic. The correlation coefficient is called R. So that's what we're going to learn how to do in part 2 of this lecture. So both of these strategies allow us to look at the strength and the direction of the relationship between two variables. So this is just an example of an interesting correlational study. Our X value at the bottom here is chocolate consumption, so how much chocolate people eat. And then our Y value up on the side is the number of Nobel laureates, so the number of people who have won a Nobel Peace Prize. No, not Peace Prize, just a Nobel Prize. And each country is actually a data point on this graph. So if we're going to fit a line to this data, and when I say fit a line, it's just an approximation of, where the data lie on the graph. It looks like countries where people consume more chocolate also tend to have more Nobel Prize winners. So this is a positive correlation. If we look at the R statistic and the p-value, which we'll talk about later, this does tell us that this is a statistically significant finding. So that's pretty interesting. And this is a real study. You can Google it. So question, can we say that eating chocolate will make you a Nobel Prize winner? No. And why is that? Say it with me, because correlation does not imply causation. Even if it makes sense, even if it's statistically significant, the only conclusion we can make is one that is very matter of fact, that countries where people eat more chocolate tend to have more Nobel Prize winners. That's all. There's a correlation. There could be a third variable we don't know about that explains this relationship. Or it could be that people who win Nobel Prizes start eating more chocolate after the fact. We don't know this because we haven't established temporal precedence. So again, all we know is that these variables are correlated with each other. All right, so scatter plots, just like the one that you just saw, scatter plots are graphical ways to represent associations or correlations. And by the way, I'm using these terms interchangeably. Association, correlation, relationship, the link between two things, these are interchangeable words. So we'll just quickly review for the types of associations you might have. And you've already seen this back when we did the claims and validities lecture. Now with scatter plots, one variable is plotted on the x-axis and one is plotted on the y-axis. we can fit a line through the data that gives us a slope. The slope shows the direction of that association, whether it's positive, negative, or if there's no association. So when an association is positive, that means that high scores on one variable is equal to high scores on another variable, as well as low scores being correlated with low scores on another variable. Negative association is also called an inverse association, and this is when high levels on one variable are associated with low levels of another variable. And then when there's no association, that's when all levels of one variable are associated with all levels of another variable. There's no discernible pattern, so they're not related. We can also use the coefficient to help us describe correlation. The statistic for correlation is R, which we will learn how to compute later in part 2. So the value of R ranges from -1 to +1. So R tells us the direction of a correlation. If R is positive, then we have a positive correlation. If it's negative, we have a negative correlation. R also tells us the magnitude of the correlation, or how strong the correlation is, how strong that relationship is. Again, the values of R range from -1 to 1. A value of 1 implies a perfect 1-to-1 correlation. The closer you are to 1 or -1, the stronger the association. So we do have some criteria for determining just how strong a correlation is. If an R value is 0.1, and that's a small effect size or a small correlation, that means the correlation between those two variables is not very strong. If R value is at least around 0.3, then this is a medium effect, or some might say a moderate effect. So the strength of the correlation between the two variables is moderate or medium. And then if the R value is 0.5 or higher, this implies a strong correlation between two variables. And again, we're talking about the absolute value of the correlation here. So whether you have an R of 0.3 or -0.3, those are still medium correlations. So some quick practice here based on these 4 scatter plots. See if you can guess which of the 4 correlations listed on the right, which one of the 4 coefficients matches up with which scatter plot. You can pause and do that, and then I'll show the answers on the next slide. Okay, so for graph A, this looks like there's somewhat of a correlation, but I can tell that it's not super strong. So I'm going to say that R equals 0.46 fits here. It looks like a pretty moderate correlation. For graph B, this correlation seems pretty strong because the points almost form a straight line. So I know that this is a really strong correlation. And I also see my points going downward. So I also know that this is a negative correlation. So negative 0.96 fits there. See that that's close to 1. It's close to a straight line. It's close to a perfect correlation. For scatter plot C, there doesn't seem to be a correlation there. All of the plots are all over the place. So I think that R equals 0.03 fits there. It's very small effect size. If any, it's actually close to 0, having a 0 correlation. And for graph D, there does seem to be a pretty strong correlation. And I see that the plots are going upward, indicating a positive association. So I picked 0.78 for that one. Here's another quick practice. You're going to put these 5 correlation coefficients in order from weakest to strongest. So you can pause now to do that. Okay, so here are those answers. Just always keep in mind that when we're talking about the strength of a correlation, we're referring to the absolute value of that number. Okay, so here's some practice on making a scatter plot. We're going to make a scatter plot to show the relationship between number of hours spent studying and the test scores that people got on a math test. So we have 6 people in this data set. So let's go ahead and make that scatter plot. So we're going to have our hours of study be our X value, and we'll plot that data on the X-axis. And our test scores are going to be our Y value, our Y score. So we'll plot that on the Y-axis. We want to see if these two variables are correlated. I have 6 participants in the study, so I'm now going to plot those 6 data points. The first person has 3 hours of study and got a score of 25 on the test. So that data point is going to be somewhere around here. The second person studies 2 hours and got a 17 on the test. So that data point is going to be around there. For the third person, I'm going to match up 1 on the x-axis and 11 on the y-axis for a data point that's there. And then here are the next 3 data points. All right, the next step is going to be to draw a line through these data. And again, this is an approximation of where the data lie based on these points. So I can approximate a line that looks something like this. And looking at this, I can tell this is a positive association. To me, it looks like a pretty strong correlation. So I can conclude here that more hours of study is correlated with higher test scores. That brings us to workshop number 9, and it's pretty much the same setup as the practice we just did together, but of course there's different data, and now you're looking at the correlation between test scores and hours spent on social media. So you know what to do for workshops. You can go ahead and pause to do that now, or wait until the end of this lecture. It's up to you, but I'm going to go ahead and move on. Before we go on to part 2, I want to talk about moderator variables. So when the relationship between 2 variables changes depending on the level of another variable, that other variable is called the moderator variable. So for example, let's say you have a correlation between stress and depression, and this might be a positive correlation, meaning that more stress is associated with higher levels of depression. That's a general correlation, right? But maybe for a person who has a lot of social support, the relationship between stress and depression might go away. In that case, social support moderates the relationship between stress and depression. So here's an example. This is what that would look like. So you see the general line for stress and depression is a positive correlation, but if someone has high social support, that's what SS stands for, then maybe that's a 0 correlation and stress is not related to depression. Or let's say they have very low social support, so they don't have a lot of social support. That might even exacerbate the association between stress and depression, not having social support to rely on. So in other words, the correlation between stress and depression depends on the moderator. The association between stress and depression depends on how much social support someone has. Let's look at another example. So in general, you could establish a correlation between exercise and weight. So maybe that's a negative correlation, meaning that when you exercise more, then you weigh less. That's a general correlation. But if you have a high caloric diet, for example, let's say if you're eating a whole bunch of chocolate trying to win a Nobel Prize, then that might change the association between exercise and diet. In other words, that original correlation, the association between exercise and diet, depends on, the original correlation, the association between exercise and weight would depend on the diet. That makes diet the moderator. The diet is going to change the association between exercise and weight. If you had a good diet, then the correlation between exercise and weight might even be stronger. So that might be a steeper correlation, a steeper line. If you had a bad diet, then maybe that association might be a little bit more weak. So now is a good time for a break if you need one before we move on to part 2 of this lecture. All right, so let's jump into part 2 where we're going to learn how to compute the correlation coefficient, or what we call R. So here's a reminder of our steps for null hypothesis testing. Step 1 is to state the hypotheses. And when we do correlational research, we do need to establish the direction of the hypothesis. So whether it's one-tailed or two-tailed, and I'll explain that in a little bit. Step 2, we're going to set our criteria. In other words, we're going to find the critical value, which, again, is our threshold for significance. And then step 3, we're going to have our data and compute the sample statistic. In this case, we're computing R. Step 4, we're going to make a decision about whether to reject the null or retain the null hypothesis based on our comparison of R versus the critical value. So with correlational research, there are two types of hypotheses. One-tailed tests are also known as directional. And in this case, the hypothesis is specific about the direction of the association. That's why it's called directional. So we specify whether it's a positive or negative correlation. So remember that the distribution for R is a full normal distribution, ranging from -1 to +1. So when you specify the direction, you're pinpointing one side of the distribution, as shown in these illustrations here to the right of the screen. So it'll be on the right tail if you're hypothesizing a positive correlation. It'll be on the left tail if you are hypothesizing a negative correlation. A two-tailed test is non-directional. The hypothesis does not specify a direction. So this might be a case where the researcher is simply testing whether or not two variables are correlated. They think that there is a relationship between the two variables, but they haven't made a specific guess about how they're related. So in that case, you are testing the full distribution and allowing for your hypothesis to be either negative or positive. So before stating the hypothesis for correlation, you must figure out if it's one-tailed or two-tailed. That's a very important step, especially when we try to come up with our critical value. So let's consider this example. An instructor suspects that the number of hours his 6 students spend studying is correlated to their math test scores. So we need to figure out if this is one-tailed or two-tailed. Well, the instructor suspects that these variables are correlated, but doesn't specify in what way. So we can classify this as a two-tailed prediction. The instructor has not specified if he expects this to be positively correlated or negatively correlated. So it's two-tailed. So now let's state our hypotheses. And again, sometimes it's easier to state the alternative first. The alternative hypothesis is simply going to be that there is a relationship between number of hours studying and the score on the math test. And the null hypothesis is that there's no relationship between those two variables. So now we're at step 2. It's time to set our criteria. Again, we'll be using a chart to find the critical value. You can see this chart in your formula packet. And make sure you're looking at the right chart. So this is for Pearson's correlation for correlation critical value. So here's the list of the information we need to know before we're able to read that chart. We need to know if it's one-tailed or two-tailed hypothesis. We need to know the alpha level or the significance level, and we need to know the N, which is the sample size. So we've already established that the example we have is a two-tailed hypothesis. We can establish an alpha level of 0.05 because we haven't been told otherwise. That's kind of our default. And our sample size, or our N, was 6 students. So we have all the information. Now we're ready to read the chart and find the critical value. Here's our chart. You just have to know where to look to find all the information. So here's the N. You'll look in that first column to identify where your sample size. Here you have to figure out where to look, if it's one-tailed or two-tailed, and then also you will reference the significance level or the alpha level. So based on the information that you know, you can try to pause now and see if you can find the critical value in this chart. Okay, so our test is two-tailed, and we have an alpha level of 0.05, so I can find that in the chart, and then our sample size is 6. So I follow all of these criteria down to find our critical value of 0.811. And then it's 0.81 when we round 2 digits to the right of the decimal. This is the R distribution. R can range from -1 to +1. Because our hypothesis is two-tailed or non-directional, our critical R can either be positive or negative. So technically, our critical value is actually plus or minus 0.81. It can either be negative 0.81 or positive 0.81. And that's a threshold for our critical region. So really, in this case, we have 2 critical regions. It's two-tailed. If we compute an R statistic that falls within either of these critical regions, then we'll be able to say that our result is statistically significant. So let's go ahead and figure out how to calculate that R statistic so we can find out. All right, so here's our data, and this should look familiar from part 1 of this lecture. So we're looking at the correlation between hours of study and test score. Here is the formula to find R. And so this is how we read the numerator. It's the sum. Remember that the sigma sign means sum. So it's the sum of the z-scores of x. That's what z sub x means. Multiplied by the z-scores of y. And we refer to all of this as the sum of multiplied z-scores. So in our denominator, we just have n minus 1. So that's pretty simple. We already know what our n is, and so that should be simple to find. We'll come back to that later. Let's deal with that numerator first, the sum of multiplied z-scores. Don't be intimidated by this numerator. We will break it down step by step. So we have two variables. We're going to make our hours of study our x variable. Test score is going to be our y variable. Now, because we have these two different variables, they're rated on completely different scales. We want to standardize them before figuring out how they're correlated. And you've already learned that z-scores help us to standardize our variables to make for easier comparison. So we will compute the z-scores for x for everybody's hours of study, we'll get a z-score. Then we will compute the z-scores for the y variable, which is each person's test score. So we will compute those z-scores, and then we will multiply the corresponding z-scores together. So each person's corresponding z-scores, we'll multiply them together. And then we're going to add all of that together, get the sum. That's the sum of multiplied z-scores. And then finally, we're going to divide that by n minus 1 in order to solve for R. So those are our steps. Again, we're going to walk through it together. All right, let's get started. Here is the formula for R. And we need the formula for z-scores because we'll be computing z-scores. And so to find the z-score, you subtract the mean from each value and divide by the standard deviation. So we need that information. So I've already have that for you here. We have the mean and the standard deviation for each variable. The mean for hours of study is 3 and the standard deviation is 1.41. The mean for test scores is 20. The standard deviation is 5.37. So you have that information available. So to help us out, we can set up a chart like this one in order to organize each step of the formula. First thing we'll do is calculate the z-scores for hours of study. So that's z sub x. Then we will compute the z-scores for test scores. Then we're going to multiply those values together. And then we will add up that last column. And that's how we'll get the sum of multiplied z-scores. And finally, we will divide by n minus 1 in order to get R. Okay, starting with the z-scores for hours of study. And I'll reference the z-score formula at the top. So let's get started with the first person for the first row of data. So that value is 3 and the mean is 3. So in this case, I'm going to do 3 minus 3, which is 0. And then I'm going to divide that by the standard deviation, which is 1.41. So 0 divided by 1.41 is 0, of course. So that one was pretty simple. Moving on to the next row of data. First, we subtract our mean from our value of 2. So the hours of study is 2 and the mean is 3. So 2 minus 3, and then I get negative 1, and I'll divide that by 1.41. And that gives me a z-score of negative 0.71. Now for the third row, that person studied for 1 hour. So I'm going to do 1 minus 3, and then so that I get negative 2, and then I'll divide by 1.41, which is the standard deviation. And then I get a z-score of negative 1.42. So you can pause right now and try to find the rest of the z-scores on your own before moving on. Okay, so now we'll just do the same thing for our next variable. We're going to get the z-scores for test scores. So first up, we'll do that first row. So we have the test score is 25, the mean is 20. So I have 25 minus 20 gives me 5, and I'll divide that by the standard deviation of 5.37, and I get a z-score of 0.93. For the second row, the person's test score was 17, so I subtract our mean from that, which is 17 minus 20, I get negative 3. Divide that by the standard deviation, and I get a z-score of negative 0.56. So again, same process for the third row of data. Here again, I'll do 11 minus 20. I get negative 9. I'm going to divide by the standard deviation of 5.37. And that gives me a z-score of negative 1.68. So again, this is a good time to pause and try to find the rest of those z-scores before moving on. So here are the rest of the z-scores for that variable. All right, we're almost there. The next step is to multiply the z-scores together. So the first row should be easy because we have a 0 there. We have 0 times 0.93. That gives us 0, of course. For the next row, we will multiply negative 0.71 times negative 0.56. That's going to give us 0.40. And for the next row, we will multiply those two z-scores together. That's going to give us 2.39. So you can pause to do the rest of these rows, which shouldn't be too hard because 2 of those rows have 0, so those will be easy to compute. All right, next we're going to find the sum of multiplied z-scores by adding up all of those numbers in the last column. So if you add up all those numbers in the last column, you should get an answer of 4.11. So that is the sum of multiplied z-scores. Now we have our numerator. So we have 4.11 over or divided by n minus 1. So figuring out n minus 1 is easy. We know that our n is 6. We have 6 students in the data set. So we just plug that in. 6 minus 1 equals 5. So now we just calculate 4.11 divided by 5. And our answer you should get is 0.82. So we have successfully calculated the R statistic. This value, if just looking at it, lets us know that we have a pretty strong correlation and that this correlation is positive because we've gotten a positive value and it's higher than 0.5, which indicates a strong correlation. But we still have to figure out if it's statistically significant. That brings us to our last step, which is to make a decision. So to do that, we need to compare the R value that we got to our critical region. If R is greater than our critical value, then we can reject the null. We can say that our correlation is significant. If R is less than or equal to the critical value, we retain the null hypothesis and it's not significant, meaning there's no relationship between the two variables. So here's our distribution. Remember that our critical value was plus or minus 0.81. Our calculated R statistic that we just computed was 0.82. And that is higher than our critical value. Only slightly, of course, but it's still higher. So if we were to put that on our distribution here, it would be on the right tail because that's a positive number. It'll be somewhere around here. So it's definitely within our critical region. So our result is statistically significant. There's a positive association, and we can reject the null hypothesis. So we interpret this by saying there is a statistically significant positive association between number of study hours, and the score on the math test. I just want to point out here that let's say, for example, hypothetically speaking, if we were to calculate R equals 7.7, 0.70, let's say that was our statistic, that would be lower than our critical region, and it wouldn't be statistically significant. But if you were to just interpret the strength of that correlation, it would still be a strong correlation because it's higher than 0.5. I'm just saying this to illustrate how something can look like it's correlated but still not be statistically significant. So now we'll walk through another practice exercise. A researcher suspects that the number of hours spent on social media is negatively correlated with student scores on a math test. She collects the following data. So this data should also look familiar from part 1 of this lecture. We are just going to walk through the same steps just like this. We'll have a hypothesis, we'll set our criteria, we'll compute our R statistic, and then make a decision. So our first step is to figure out if this hypothesis is going to be one-tailed or two-tailed. Well, if we look at this again, the researcher suspects, or that's just another way to say hypothesizes, that the variables are negatively correlated. So this is definitely one-tailed. There's a specific direction hypothesized. This is a one-tailed hypothesis. Now it's time to set our criteria. Again, to do that, we need to know if it's one-tailed or two-tailed. We need to know our alpha level, our significance level, and we also need to know the N, or the sample size. We just established that our hypothesis is one-tailed. We know that our alpha level is 0.05 because that's our default, and the N is 8 students. If you looked at our data sets, we have 8 students in the data set. So you can pause now to see if you can find the critical value on your own within the chart. So again, our hypothesis is one-tailed. The significance level is 0.05. The N equals 8. So if I follow that information, I get a critical value of 0.621 or 0.62 when we round. Specifically, our critical value is negative 0.62 because again, the researcher suspects that there's going to be a negative correlation. This is a one-tailed test. So our critical value is to the left of this distribution. So it's negative 0.62. So here's our setup to compute the R statistic. We already have the mean and the standard deviation set up for us here at the bottom. Here is the formula to find R. It's a sum of multiplied z-scores divided by n minus 1. So we're going to need this z-score formula in order to calculate those z-scores. So again, just to review, first we will find the z-scores of the first variable, which is hours of social media. That'll be our x variable. Then we'll find the z-scores of test scores. That's our y variable. Then we'll multiply those z-scores together, and then we will get the sum of those multiplied z-scores. And finally, we divide by n minus 1 to get R. So I'm going to walk us through the first 2 rows of data. We'll start with our first variable, hours on social media. So the z-score for the first row is going to be 0. So that person spent 0 hours on social media. The mean is 2.88. So I'm going to do 0 minus 2.88. That gives me negative 2.88. And then I'm going to divide that by the standard deviation of 2.03. That gives me a z-score of negative 1.42. For the second row, our data point is 1. That person spent 1 hour on social media. So I'm going to do 1 minus 2.88. And I get negative 1.88. And then I'm going to divide that by 2.03, and I get a z-score of negative 0.93. So now you should pause and try to calculate the rest of those z-scores for hours on social media. So here are those z-scores, so you can check your answers against what's here. Now we're going to calculate the z-scores for that second variable, which is test score. So our first data point is 15. So, and our mean for test scores is 13.75. So I do 15 minus 13.75 to get 1.25. I divide that by the standard deviation for test scores, which is 3.54. I get a z-score of 0.35. Same thing with the next row. This person got a 20 on their test. So 20 minus 13.75 gives me 6.25. I'm going to divide that by the standard deviation, and I get a z-score of 1.77. So you can pause now to find the rest of those z-scores before moving on. Okay, so here are the z-scores for test score, so you can check your work against that. Now the next step is to multiply the z-scores together. So again, I'll do the first two rows to demonstrate. For that first person, I'm going to multiply negative 1.42 times 0.35. When I do that, I get negative 0.50. For the second person, I'm going to multiply those z-scores together, and I get negative 1.65. So again, you know the drill. You can pause here to finish off that column. All right, here go all of the multiplied z-scores. Now we need to find the sum. So in order to do that, we will add up that last column. So add up all the numbers in that last column. Be sure to pay attention to where you have negative numbers. So once you add up all those numbers, you should get negative 3.37. So that's the sum of multiplied z-scores. That's the numerator to our formula for r. So we're not done yet. Now we have negative 3.37 divided by n minus 1. So we know that our n is 8, so we just plug that in for 8 minus 1. And when we do that, we get 7. So ultimately, we'll be dividing negative 3.37 divided by 7. And that's going to give us negative 0.48. So that is our R statistic. It's negative 0.48. Just by looking at that, I know that there's a negative correlation between these variables. So that's aligned with the hypothesis, but we still don't know if it's statistically significant. I can also tell just by looking at the R coefficient that it's a moderate correlation. It's almost strong because our threshold for strong is 0.5. So it's a moderately high negative correlation. But again, we don't know if it's statistically significant yet. So let's get on to that. So time to make a decision. Remember that our critical value is negative 0.62. That's the threshold for significance. The R value we just calculated is negative 0.48. So that is moderate, like I said, but it's not within our critical region. It is lower than our critical value. So that correlation is not statistically significant. We have to retain the null hypothesis. So we would interpret that by saying there's no statistically significant correlation between hours spent on social media and math test scores. So that brings us to workshop number 9. The information you have here is pretty straightforward. I didn't even give you variable names. It's just X and Y are the variables. It's a pretty small data set. The sample size is 4, n equals 4. And I wanted to make this fairly simple so that it would be easy to practice. Even if you don't plan on submitting this workshop for credit, you should definitely still do it for practice for the test. So the information given here says that the researchers are testing a non-directional hypothesis to see if two variables, X and Y, are correlated. Use 0.05 for alpha. So this information tells you that this is a non-directional hypothesis, which lets you know that it's going to be two-tailed. You have an alpha level of 0.05. So with that information, you can find the critical value. You have two-tailed, n equals 4, and alpha equals 0.05. So you can find the critical value in the chart. And then you can set up a table just like what we've been doing in practice during lecture to find the sum of multiplied z-scores. And that's the answer to that question is just going to be the numerator for the formula for R. And then the fourth question says, by what number will you divide the sum of multiplied z-scores? That's just asking you what's your denominator of that formula. So we know that our denominator is n minus 1. N equals 4. 4 minus 1 equals 3. So that's the answer to that question. So our denominator is 3. That's what we're going to divide the sum of multiplied z-scores by 3. And then we calculate R. So you'll go ahead and do that process. And then finally, you'll make a decision. Compare your calculated R value to the critical value to determine if your correlation is significant and what conclusion you can make about variables X and Y. In other words, you're just going to say, are X and Y correlated? If so, what is the direction of that correlation? Is it negative or positive? If as a bonus, you can go ahead and include like what's the strength of that correlation. Is it small or weak? Is it moderate or strong? All right, that's it for today. Please be sure to email me with any questions you might have. And that's all. Take care, everyone.